Okay, folks, so we are at the very last section of chapter 3 on something called the evidence approximation. Now, this section is coming at the end of the chapter, and I think it's quite an advanced section in lots of ways. So I think you can actually safely skip it if you want, if you're, let's say, pressed for time or whatever it is. There are a lot more, I think, top of the line topics that you need to learn in the book than what's covered here. Nevertheless, I think if you do want to stick around, I think there are actually some really interesting ideas that are kind of very broadly relevant that are contained in this section. So what I'm going to do in this first video is first just kind of give you a sense of where this section is, going, and what some of the cool ideas are going to be. And then in the subsequent videos, then of course, we'll go through each of the sections individually. Okay, so the very first, the whole aim of this section is we're interested in computing a particular integral. So when you're doing Bayesian things, you're often having to integrate over lots of variables, and that is almost always going to be hard to do. And so these days, folks will sometimes resort to using kind of numerical methods because we have fast computers. But back kind of in the 90s, in the 80s, when these ideas were coming up, you wanted to do Bayesian things, but you didn't necessarily have the computational power to actually necessarily compute some of these very large integrals. And so people started looking at doing, how to approximate these integrals, and ideally maybe getting some kind of analytically tractable answers. So the idea here that we're going to use is, look, we're going to have this big integral that we want to do, and now we're going to approximate it by replacing this term, which is kind of problematic, and it's kind of some function over these two parameters, alpha and beta, with just its value at its peak. And so we're going to try to approximate this by getting rid of this integral, or simplifying, you'll see how, and replacing these alphas and betas by their values at their peak. So we'll see it's kind of like putting a delta function at the peak values. And so that in itself is a very powerful technique of when you have a hard integral, trying to approximate it by taking a problematic term and replacing it by its peak. Now, it does not necessarily always work, and you have to kind of check that it does, and we don't actually check that really very much here in this section. But that is the first cool idea, having a kind of complicated integral and replacing it by its value at the peak. And that's basically what's here, and that's kind of one of the key ideas that's just generally useful if you're doing, if you're reading or if you're doing research in your own work, etc. Okay, so that's in the first. Now, okay, so now it turns out, well, what is this thing that we're trying to approximate? We need to find its maximum, and so it turns out that this is actually related to something called the marginal likelihood or the model evidence. That's where this term evidence function comes from. And so in this section, we actually derive an expression for this marginal likelihood, this evidence function, and we can do that because we're working kind of a linear Gaussian setting, and so things are simple. In general, they won't be so simple, but in this particular case, we can do it, and we get some insightful answers. So this function is just kind of cool to know about. And we end up getting an answer kind of right around here that says, look, the marginal likelihood, which is kind of essentially is saying, what is the probability of your, the model evidence? What is the evidence for what is the probability of your model, basically, when you integrate out over all of its parameters? Turns out to have a really nice interpretation in terms of a kind of a goodness of fit term. So how well can your model class in general fit the data? And then some kind of complexity parameter, which is trying to penalize more complex models. So that's kind of one of the advantages of the Bayesian approach. You get these complexity balances just showing up, also called Occam factors for Occam's razor, showing up naturally. And so we'll see that we can actually compute that in kind of closed form for our very simple model. And then we can kind of, as an aside, we can actually do this really interesting thing where we look at, one of the parameters we've had here is kind of the order of the polynomial that we're using to fit our particular data set. It turns out it has a kind of very interesting shape that we can kind of then make sense of using the marginal likelihood, also known as the evidence. So this kind of middle section is just about this concept of the marginal likelihood. and then using it to kind of, pick your model order. The cool thing about it too is that, you imagine in a normal setting when you have to kind of pick a model order, what you have to do is you have to, like, you have some training data, you use it to like learn the best parameters, and then you use like kind of the left out data to figure out what the best model order is. And we did that kind of back in chapter 1. So the cool thing about this is you can actually compute this just on the training data. So you don't actually have to do this whole cross-validation thing. You can actually figure out what your model order is just using training data. So that's kind of a useful property in and of itself. And that's something where even if you can't necessarily come up with a closed form term, if you can kind of evaluate it numerically, the simpler integral numerically, then you can still kind of carry this out. So it's to use your training data to kind of determine some of the parameters that you need. Now, one key aspect here is that we'll get that when we get to it. So okay, so now once we've got that evidence function, the whole idea was, remember, we wanted to replace this with this maximum. And so in this particular section, we do that. And the cool idea that shows up here is actually twofold. One is that, well, how do you maximize things? You set the gradients to 0. Well, when we do that, it turns out that we don't get kind of a closed form answer because the parameters we're after kind of show up kind of everywhere. So we can't kind of isolate them. So the interesting idea in this section is that of bringing in kind of these iterative procedures for numerically determining the parameters that you need. So that's kind of what we do. We come up with these equations for these alphas and one for beta, down here. Now it turns out, for example, in alpha that you need the alpha shows up in gamma, and it's also in there, and it's also in M. So you can't solve this, analytically. So what you do is you essentially kind of start with some initial value of alpha, and then you plug it into these other guys, and then use this ratio to determine alpha, and so on, and so forth. So you get this kind of iterative procedure. So that's, again, a very general tool that you should just know about, that you can do. Again, it doesn't give you a kind of a closed form answer in the most cases, but it gives you a procedure for figuring out, the parameters you're after. Okay. And then in this, I'm just wondering. Oh yeah, and there's kind of one other idea that comes up here, which I thought was cool. I hadn't occurred to me, but when you're kind of doing this, when you're computing these derivatives, just the notion that a variable is kind of linear in the one you're interested in means that you can replace this derivative with a particular ratio, which allows him to kind of solve for things. So again, that's kind of a bit of maybe kind of an obvious idea, but hadn't occurred to me, and I really liked it. So I think it's a good one to know about. Again, very useful generally. Okay, finally, in this very last section, we're going to talk about this idea of the effective number of parameters. So the idea is that we're going to look at the likelihood function for our parameters. I'm going to kind of look at its, we'll do an eigendecomposition on it, and we'll essentially be able to come up with a number that actually has already shown up in this kind of gamma value that essentially tells us how many of our parameters, of our m parameters, however many it is, are well fitted to the data, and how many are kind of being dominated by the prior. And that's kind of just has to do with how big these, we'll see these kind of the precisions of this, the covariance or likelihood function look like. But again, I think this is a very interesting and useful interpretation of the parameters that you get, and you'll come across this a lot. We saw this object, the overlap with the features, and now we can kind of analyze it, to understand, use it to kind of get a sense of how much of how well our data is actually constraining our parameters. So I think this is kind of a very, very cool idea, and very kind of probably quite useful to know. And that's about it. And then so at the very end, we do some very basic checks that this whole thing kind of works. I think we could do more. And then that's basically the end of the chapter. So I think it's quite again, I think I would say probably the most advanced section that we've come across so far in the book. You don't have to read it on the first pass, but if you do, I think there are some really cool ideas that we're going to discuss. So, and I'm going to actually put some resources. I've taken some notes on this chapter myself, so I'll post those. There's a paper that kind of goes with this chapter, which is based on, from 1992. It's actually the paper by Mackay, so I'll post a link to that. It's also very readable, lots of interesting ideas there. Also, there is, I found online, there is a series of kind of video lectures from a researcher in Amsterdam who's kind of covering exactly this book in a kind of a slightly different way. So again, useful to you guys can have a look at that, get a kind of different perspective. Always good to have multiple perspectives whenever you're learning something. So I think it'll be fun. It'll be fun few topics to discuss together. So yeah, hopefully you'll join me. Again, you don't have to for this section, but I think if you do, there's a lot of fun stuff to cover. So yeah, so hopefully we'll I'll see you there in the next video. Bye for now.